So this talk is maybe going to be a little less polished. Not that my last talk was polished, but this might involve more me jumping around and being excited.
Why, Dylan?
Huh?
Why?
Because there's so much to be excited about on Yes, with Morava E theory and Morava K theory. Just you wait. But I thought that we would start, since this is a chromatic homotopy theory conference, by writing down a map between two spheres. I don't know if you all knew this, but this is what we're here for. We're supposed to be finding all of these, right? So there's various tools that we have to try to find all of these. One thing that we can do is we can take this map, G, and we can produce a map on any cohomology theory applied to both sides. So this induces a map from a shift, say E star shifted by K, to E star, if E is a cohomology theory. And this is a first test to see if the map is not zero. If this thing is not zero, then the map is not zero. You can tell how much I prepare. Yeah. Okay. I really have a lot to say about this. So this is a first attempt to try to show that this map is not zero. But if this thing is zero, we're not done. There's another thing we could try. So I don't know what to call this. Let's call this D of G, because when E is H, this is the degree of a map, where if K is larger than 0, define the degree to be 0, because that's what the map is. And if K is equal to 0, then this is the degree of a map between spheres on, say, homology. So if this is 0, we don't give up. Then we can try something. So we can extend this map. We can take the mapping cone. So we can use this to attach a K+1 cell. And this space knows something about this map, and we could try to understand how non-trivial this space is when we apply a cohomology theory to it. So if we apply E star to this cofiber sequence, then we get E star shifted, E star of this thing, and then E star shifted, and the next term is E star shifted again. But I want to point out that we're assuming that the degree of G is 0. So this map is 0. So let me just put a 0 here. And this map is also 0. So this is an exact sequence. So this is an exact sequence of E star modules, if E is a ring spectrum. But this is an element. This is some extension of an E star module. It's an extension of E star K+1 by E star. It's an extension in what, though? What category is this an extension in? Well, we saw that it's useful to think about, for example, cohomology operations acting on all of these things, or dually, co-operations co-acting. Not that that's really a verb that makes sense. But so this is really happening in E star E comodules, by which I mean that each of these things is an E star E comodules, and this is an exact sequence in that category.
What was the assumption that let us turn this into 0?
Yeah, so the map, I mean, the term isn't 0, but the map is 0. Okay. So this seems like a pretty good idea. So why don't I give some examples? I gave some examples of D. So if E is equal to, say, HF2, and you wanted to figure out if the hop map was not 0, then one thing you could do is you could take the cofiber of eta. And if you hit this with HF2, then you get the homology of the sphere, the homology of the cone on eta. Why don't I do cohomology, because it's easier to draw. And thank you. Okay, so this is an exact sequence of, since I'm doing cohomology, this is an exact sequence of modules over the Steenrod algebra. And this is a fairly silly module. It's the trivial module. This is also the trivial module, but it lives in degree 2. And this is, as a vector space, 2 copies of F2s. This is a trivial exact sequence of F2 vector spaces, because every exact sequence of F2 vector spaces is trivial, but there's a cohomology operation, square 2, which is telling this class to go to this class. So this is a non-trivial extension of modules over the Steenrod algebra. So this is an element in X1. Let me go back to homology for a second. H star shifted by 2 and H star, which is often called H1. And this is the Hopf element in X1. So this is some element in X1 which wants to detect a map. Okay? And it succeeded. It saw that this map was not 0. So in general, we can keep trying to do this. We have a sequence of invariants to test against, starting with just the induced map on homology. Then we get this extension class. And if that extension is trivial, it's possible to find a further invariant living in X2, and so on. And we could hope that at some point those are non-zero. And if it's non-zero at some point, then the map was not 0. So we get invariants, or a sequence of invariants of a map, Sk to S0, living in X S. Turns out you have to shift by this much. So this turns out to be where it lives, and this is X in the category of E star E comodules. Okay? And this is trying to detect this map. And it turns out you can turn this procedure around. You can start with some elements in here and ask, do they detect a map? Is there a map in homotopy that realizes this invariant? And that question is called a spectral sequence. And it's trying desperately to answer this question. Its job is to start with this conglomerate of groups and attempt to converge to the homotopy groups of spheres, but you shouldn't really take this arrow seriously at this point. So this thing, a better answer for what it's trying to converge to is that at most this thing is going to see what E sees about all of homotopy theory. And we saw last time a good way to take homotopy theory and talk about what does E know about homotopy theory, which is the localization. So this is still technically a question mark, or quotes should go here, but this is honest enough of an answer that I'm going to unquote it. So this is attempting to converge to the E localization of the sphere and the homotopy groups of the E localization. This thing is called the Adams-Novikov spectral sequence. And if our talk were in more historical order, we probably would have started with something like this. This is the thing that we want to try to compute. And when E is HF2, this is the HFP, this is the Adams spectral sequence. And when E is MU, this is the Adams-Novikov spectral sequence. And then we just didn't want to come up with a new name, so we also called it the Adams-Novikov spectral sequence for all other E. So what we'd like to do is eventually compute the homotopy groups of spheres, which is too hard, so we accept a localization is just fine. And the first approximation to a localization is going to be this piece of algebra. And it's just algebra, so how hard could it be? So, all right. So that's where I wanted to start. And I want to point out that what we've been discussing is a lot of the algebra of mu star and mu star mu comodules. So in a particular example of the Adams-Novikov spectral sequence was the okay, I'm going to get lazy. I'm no longer going to put in all these shifts. Sorry. So it turns out the mu localization of the sphere is just the sphere. So this really converges to the homotopy groups of spheres. And so what we'd like to do is understand this algebra, and what I'd like to do for the beginning of this talk is try to reinterpret this algebra using the picture that Mike talked about. Sort of what is the algebra we're trying to do, and how can we think about it as computing some cohomology of some space, maybe one of those pictures that Mike drew. Okay. Any questions about just this? Okay. Okay, so the first thing that I want to say is I want to kind of revisit this pair, this pair mu star, mu. So remember, Hams out of this took a ring to the groupoid, objects were Hams out of this, and isomorphisms were Hams out of this. Groupoid of formal group laws and strict isomorphisms. And what I'd like, and Mike sort of drew a picture of this space that you get, which is like spec of mu star, and that group that was acting was really a groupoid, and it's spec of this thing. And he drew for you a picture of this space. If I think about it purely in algebraic geometry and just think of sort of the set of prime ideals and take this quotient, then we get this picture with a point for each prime and each height at each prime. So maybe these are the primes. Do you really need to know the names of the prime? I'm not really going to do anything here except have these points. So I'll write the next thing bigger. But it's not important that this is a 2 and this is a 3. Okay. So, right. So the point is just, right, so this is the picture that you get if you sort of do this set theoretic thing of taking isomorphism classes of formal group laws. But I would like to do something, we're homotopy theorists, and so maybe a thing that we might do instead is, instead of taking two formal group laws as points in this groupoid and calling them the same if there's an isomorphism, we should just draw a path that's telling us that there's an isomorphism. So I want you to think more that this object wants to be a homotopy quotient. So instead of modding out by an equivalence relation, we're going to draw in a path for each. Draw a path for witnesses of an equivalence. And then I want to think again about what it means to map in to this space. This sort of thing is a space, and it's going to be called MFG. This is the moduli space or stack of formal group laws, or formal groups, if you want. And what I want you to think of it as is it's like the classifying space of this groupoid, except you have a groupoid for every R now, and you have to do algebraic geometry and figure out how those all piece together. But it wants to be the classifying space of this groupoid for every R. And what that means is that if I'm trying to map into it, then a map into this space is picking out a point of this space, and a point of this space is going to be an isomorphism class of formal group law over spec R. Or maybe if I'm thinking about this as an honest space, I choose some actual model for this homotopy quotient, then this is really seeing an actual formal group law over R. So this is the data. A map, whatever this thing is, map from spec R into it is the same as a formal group law over R. But the reason why I bring up this idea of paths is that if you have two maps, if you have a diagram like this, then you don't just want to say what it means for a diagram like this to commute and say something about formal group laws over R and R prime. You actually want to choose a homotopy between these two maps. These are like two different maps into MFG, and you want to choose a path between their value at each of their points from one to the other. I'm going to depict that like this. So this is the picture to have for the data of a formal group law F over R, a formal group law F prime over spec of R prime, and this choice of homotopy gives you a choice of isomorphism of F prime tensored to R and F. So this is a specified strict isomorphism of formal group laws.
Is the map from R prime to R, we already have those?
Yeah. So if you're given that, yeah, I could give this a name. We're using that here. But I'm saying some of the data of a diagram that I draw like this is the data of two formal groups over these different rings, a map from one ring to another, and then the base change of one is the other.
Can you write
Oh, why don't I give it a different name? What's another name for a ring? S is, okay, S is fine. Yeah, that's okay. Is that okay? Huh? It's too late. We've committed. We've committed to S. Okay. All right, so the reason why I bring this up is because, why is the reason I bring this up? Right. So I'm moving towards trying to understand mu star mu comodules. So I'm trying to build up this geometric point of view. And really, so I said this out loud, but maybe I should put it in writing. MFG classifies, is like a classifying space for formal group laws. So it classifies formal group laws, but maybe something that fits with our intuition a little bit better is that what it really does is it classifies what I want to call bundles of formal group laws. Because spec R is supposed to be a space, and spec R has a lot of points in it. It has a point, anytime you hand me a map from R to a field, spec of a field has just a point, and that picks out a point of spec R. And so a map from spec R to MFG is really picking out for me a formal group law over a field for every residue field of R. So when I write this, alpha classifies a formal group law over R, which in particular produces a formal group law over K of P, the residue field, for each prime ideal P in spec of R. Well, K of P is the name of the residue field. So you localize at the prime and then you mod out by it, right?
So when for every, if you're going to get a field, it has to be a maximal ideal.
Right. So you localize at the prime, and then the prime ideal in the localization is maximal, and then you mod out by it. So it's a residue field. But if you like, you could also just look at the maximal ideal. Yeah. Okay. So you're getting one of these bundles, and so the reason why I bring this up is because I want to say that we've been thinking about formal group laws over spec R, and we've been drawing these pictures of formal group laws, and we have these points. And I think it's worth pointing out that the points in algebraic geometry are spec of fields. Spec K, where K is a field. And K is maybe even an algebraically closed field. And so I want to reinterpret the picture that Mike drew of the points. So what does it mean when we say that MFG looks like, let's localize at a prime, and then it looked like just a sequence of points where this direction is the height. So I'm going to reinterpret this as a theorem, which is classifying for you what are all the ways that you can map in a point to MFG. So this is a theorem, I think, of Lazard. It says that over an algebraically closed field, of characteristic P, height is a complete invariant of formal group laws. I think Mike said this out loud maybe, but didn't write it down. But I wanted to point this out. So this is what we mean when we draw this picture. We're drawing the picture of the points, but this is supposed to be a space, and these points are somehow glued together in some non-trivial way, and so you have to, if I could try to draw a picture of the real numbers by drawing a point for each real number, but it wouldn't really be, it wouldn't tell you about how they're glued together. Yeah. Okay. So now I want to, right. So that kind of justifies the picture. I want to make one other point before I move to these co-modules, which is that this is a remark. Maybe this is an aside, which is that over Z localized at P, the P series of F determines F. So this is the reason why. So the P series of F determines F, and the P series is determined by those turns out by those VIs or some other choices of those VIs, if you like. And so we have these two groupoids, this BP star BP and this MU star MU localized at P. And the point is that these things are for every ring, I can hit the ring with these functors, and I get groupoids, and these two groupoids are equivalent. But this actual Hopf algebroid, these are like very different. This one's much bigger than this, but somehow emphasizing the fact that we just care about this moduli stack, not the actual way that we're telling you this groupoid. Like, we're giving you this groupoid by specifying all of its objects and all of the isomorphisms between them, but we could have chose some specific isomorphism classes of objects and isomorphisms between them, and as long as that is an essentially surjective functor and you see all the isomorphisms, then you're talking about the same problem. So what I want to convince you now is that MU star MU comodules, and in general comodules, are really something to do with this stack and not something to do with specifically the structure of MU star MU as given and BP star BP. Do you have a question? Yeah, equivalent groupoids after applying Hams of rings into R for all commutative rings. Yeah, thank you. Okay, great. Okay, so now I want to justify this claim, which is that MU star MU comodules are, so the actual word is quasi-coherent sheaves, but I don't expect that word to be friendly to you. If you like, you can think about this as like vector bundles. It's like a generalization of vector bundles on MFG. Okay? e.g. So vector bundles would be an example of a quasi-coherent sheaf. So why is that? So first of all, I should say, what could I possibly mean by some type of vector bundle on MFG? So what does the second thing even mean? What does a quasi-coherent sheaf on MFG mean? Well, the point is that maybe I don't know what it means, but I know what a quasi-coherent sheaf over spec of a ring is. And if you don't know, then I can tell you right now, a quasi-coherent sheaf over spec of a ring is just a module over that ring, right? So if the ring is a field, then a quasi-coherent sheaf is a vector space, which is like this. So a bundle over a point is just a vector space, for example. Okay, so whatever it means, if I have a quasi-coherent sheaf, some bundle living over MFG, then I should be able to pull it back along any map from spec R into MFG, right? Whatever it is, if I have a sensible notion of it, I should be able to spit out a pullback. And so that means for every, but I know what a map into MFG is. That's the data of a formal group law over R. So a quasi-coherent sheaf, in particular, whatever it is it should include the data of a module over every ring equipped with a formal group law. So quasi-coherent sheaf on MFG should consist of, first of all, for every map from spec R to MFG, i.e. formal group law on R, we should have an R module. So let's call this eta. And then if I pull back and then pull back again, that's supposed to give me the same answer. So for all diagrams like this, so I have an eta here. What's another letter? Alpha. Okay. So if I have a diagram like this, but I'm supposed to choose a way to make this diagram commute, then I'm supposed to have associated to each of these diagrams an isomorphism between M alpha base changed to R and M eta. And then I expect this data to be appropriately compatible. So you don't, after you have this as like a definition, you can turn this into a definition that doesn't even, you don't even need to make sense of the object MFG. You can just remember you have this functor that spits out whatever the object is, a map into it just is a formal group law over R. And so you could just define a quasi-coherent sheaf on MFG to be the data of, for every formal group law over a ring, a module over that ring, for every map of rings, et cetera, et cetera. You can remove having to interpret this stack if you get it. But remembering this geometric language allows us to cut down on the amount of information you have to specify. If you're trying to specify a bundle, a vector bundle on some space, and you have an open cover on that space, then you're allowed to tell me what it looks like on each open set and how to glue it together on the overlaps. More generally, if you have a cover of some space by, say, a fiber bundle, you can specify the value of a bundle on the total space and also on the pullback of the total space with itself. That didn't make any sense. I'm going to write it right now. So among all maps from something affine into MFG, we have an example of one that we like a lot. Oh, maybe I should call this mu star. We have the universal formal group law. So we have a particularly good one. And this is, in some sense, surjective. This hits everything. This sees all the formal groups. And what we can do is we can try to specify a bundle on MFG by specifying a bundle here and a bundle here, and then gluing data. So it turns out that this pullback is going to be spec of mu star mu. And so the idea is that a quasi-coherent sheaf on MFG, this thing is called descent. This idea, like that thing of like having an open cover and saying transition functions, more generally, if instead of having this map be the map from a disjoint union of a bunch of open sets in, you could try to ask this question when this is some more general type of map. So quasi-coherent sheaf on MFG is the same as an mu star module plus an mu star mu module plus an isomorphism when so they have to agree when you pull back all the way to here. Oh, sorry, I did this wrong. Sorry, an mu star module and another, let's say M0, an mu star module M1, and an equivalence of mu star mu modules from M0 tensored up to mu star mu to M1 tensored up mu star mu. But maybe I should write one of these on the right. But you can't go that way. If you have a vector bundle on here, vector bundles don't push forward, right? I can't.
I mean, it seems like the hours are going. I mean, I know the hours are going. I know your hours are right because there's map mu star and mu, but at the same time, if I think of the way that one constructs projective modules over a fiber product of rings.
But it's not a fiber product of rings. There's a fiber product of spaces, so that corresponds to some sort of coproducty thing to the rings, right? Even though it's also not that, but I think you're flipping variance. Yeah, no worries. Okay, so at the end of the day, it turns out that this is actually a great exercise. So to show that this data is just the same as the data of an mu star mu comodule. So like as a hint, for example, that you could include in M0 tensor 1 to this, and this would give you a map from M0 to mu star mu tensored over mu star with, oh, you wish that was M0 there. Okay, so you better check that you can put an M0 there. And that's the coaction map. Yeah?
Could you spell what MFG was? I thought it was spec mu star.
No, right, so it's this thing. It's this funky, it's the homotopy quotient of spec mu star with spec mu star mu. Yeah. Okay. Well, the pair spec mu star mu is like a groupoid object in schemes. And yeah, I'm basically considering that groupoid object, but I'd like to do when I'm thinking about groupoids, it should be okay to replace a groupoid, say, by an equivalent one, right? And still get the same answer. So and still be able to say all the same things. So the reason why I went through all that trouble was that was that this last thing, mu star mu comodules, has to do with the way that we presented this MFG. But the first thing, or say this definition, had nothing to do with mu star mu, really. It just had to do with, do we know what a formal group law is? So a corollary of this observation is that the category of BP star BP comodules is equivalent to the category of P local mu star mu comodules. Just because the groupoids are the same. So in particular, you can compute X in either category. So X BP star BP, which is much smaller, just is the same as X mu star mu localized at P. So this is something, this is like a first example of sort of the power of thinking in this way. You can suddenly see that computations are equivalent to much smaller computations. Okay. Now I want to rewrite. I'd like to rewrite this Adams-Novikov spectral sequence in a different way. So another name for X'd BP star BP of BP star with itself is you're looking at BP star as like the unit object. You have a symmetric monoidal category. You can tensor things together, and BP star is like the unit. Yeah, sorry. Oh, this is an important point. This is why I changed from left to right. So there are two maps. So one corresponds to including this came up in Mike's talk about the two different complex orientations on mu smash mu. Right, so those lead to two different maps from mu into mu smash mu. So there you can either include in as the right factor or the left factor. And that corresponds to taking the source or target of an isomorphism in your groupoid. Okay. What are the what? Right, so in order to say what those other two maps are, I would have to say more about what I mean by the symbol MFG. And so the idea, so yeah. They're the quotient map, like the thing that's presenting it.
Like, shouldn't everything have a map to its groupoid?
Yeah, right. So if that was not, a lie, then yes. If I wasn't lying to you about, the definition of an algebraic stack or something, then sure. Sorry, I didn't mean to lose your trust. Okay, so let me just point out that BP star is the unit, the tensor unit in BP star BP comodules. And if BP star BP comodules are supposed to be like quasi-coherent sheaves or vector bundles on MFG, then what's the unit in the category of like vector bundles on some space? It's just the trivial rank 1 bundle, right? So sometimes that's called the structure sheaf. So in the land of quasi-coherent sheaves, this is O MFG and maybe localized at P. So this is the structure sheaf. The structure sheaf is the thing such that sections of it are functions on your space. And now a map from the trivial bundle into a vector bundle is the same as choosing a section of that vector bundle. Right? A map of vector bundles from the trivial bundle into a vector bundle is the same as choosing a section. So if I'm computing something like maps from the trivial bundle into stuff. This stuff is shifted around because we had all those shifts. And that's the same as computing sections of whatever this bundle is. So I'm going to reinterpret X of, say, either one, mu star, mu, BP star. This is the derived functors of Hom. So this thing is the derived functors of taking global sections of this sheaf, which is another name for sheaf cohomology. So this is like the sheaf cohomology of MFG. And then I'm being vague about the coefficients. But the takeaway that I want you to have from this is that So we started off doing homotopy theory, and we turned it into a problem of algebra, but then we realized we're homotopy theorists, we can't do algebra, so we reframed it in a way that looked more like spaces. And now we're trying to compute the cohomology of a space-ish. But let's just pretend. And if you were going to compute the cohomology of a space, how would you do it? My girlfriend's brother is an analyst, and he told me that he was like, isn't homotopy theory basically just like the Van Kampen theorem over and over again? Like, isn't that all of homotopy theory? And I had a hard time saying that it wasn't. Huh? Yeah. And I had a hard time, maybe that is what all of homotopy theory is. Because that's what we're about to do, basically, or the cohomology version of the Van Kampen theorem. If someone hands you a space and tells you to compute its cohomology, one thing you might try is the Meyer-Vietoris sequence. So let's compute the cohomology of MFG by finding an open cover. And Mike drew some pictures of some open covers, but I'm going to pick a slightly different open cover. Here we have all the points, and MFG is the union of all of its points, but that's not an open cover. So I'm going to take a little epsilon ball over each point. I wish these intersected. It's too late. Okay. Epsilon is larger now. This is a misleading picture, but we're going to try taking a small neighborhood around each point in MFG and compute the cohomology there. So now I have to make sense of what I mean by taking a small neighborhood around a point. And when I say small, I mean real small. I mean infinitesimal. So what does that mean? So now we need to go back a little bit to, so question. What is an infinitesimal neighborhood around a point? Well, whatever it is, if I were going to tell you a function on an infinitesimal neighborhood around a point, I could start by trying to tell you like a power series in some coordinates, and then hope that it converges. But, you know, every power series probably converges if you pick a small enough neighborhood. So the idea is functions on an infinitesimal neighborhood should be like power series. I.e., so e.g., we could take spec or spoof. Maybe I'll write spoof. Spoof is spec if you haven't heard of spoof. You can take spoof of, say, FP adjoint T, and this is a space which you're supposed to picture like this. It's a point with some fuzz. In the sense that the actual like points in spoof is just open prime ideals. There's only one of them. So this thing just has one point, actual point as a topological space, but functions on this space, it's a space equipped with some sheaf of functions, and functions are power series, and they want to converge in some small enough neighborhood. So this is how you're supposed to picture this. So more generally, in algebraic geometry, infinitesimal neighborhoods correspond to spoof of R, where R is, say, a Noetherian complete local ring. So it has a single maximal ideal, and modding out by that maximal ideal gives you a field, and that field, spec of it, corresponds to the point that you're taking an infinitesimal neighborhood of. Okay? So now I want to figure out what is an infinitesimal neighborhood of one of these points in MFG. Each of those points corresponds to a height n formal group law over a field. And I want to compute what an infinitesimal neighborhood looks like. So what is an infinitesimal neighborhood of a height n formal group law over an algebraically closed field inside MFG? Maybe I don't. Let me remove over a field. So I have a map from spec of a field into MFG, and I want to know I want to describe this complete, this hopefully Noetherian complete local ring, spoof of whom is the infinitesimal neighborhood of this point. So I'm going to reformulate that in terms of, since we don't really understand what this object is, I'm going to reformulate that in terms of formal group laws. So what am I actually asking for? So what I might try is I might try to just stick all fuzzy points into this spot and try to map them in and ask what's the best fuzzy point that maps to the moduli of formal groups. So search for the universal example of a Noetherian complete local ring R with a diagram spec K to spoof R to MFG. So now I'm just going to write down the, okay. I'm just going to write down what that phrase means, a universal example of a thing that fits into that diagram. So let me write down what the collection of all examples are and then hope that there's a universal one. So let me make a definition. So fix gamma, a height n formal group law over K, which it doesn't have to be algebraically closed, but it has to be a perfect field. So for example, FP. Then I'm going to define a functor, deformations of gamma. And it's going to be a functor from the category of complete Noetherian local rings R equipped with a map from R to K. So that's on spec, that's picking out a point that I want to be the neighborhood of. And I'm going to take the residue field to be K. So this is going to induce an isomorphism between the residue field and K. There's other choices, but this one's fine. So this is the category, this is the source category, and then it's going to spit out a groupoid of triples, or well, let me figure out how many n's are in the tuple. It's going to be a formal group law over R, oh no, I think I put in enough data here. It's going to be a formal group law over R such that when you tensor down to the residue field, this just is gamma. Maybe I'll even put an equals sign here. So this is a set, but maybe I want it to be a category. So I'm going to say plus isomorphisms, which are the identity mod the maximal ideal. So isomorphisms of these strict isomorphisms of these formal group laws, which mod the maximal ideal, just look like the identity. Okay, do we kind of understand what the... So this is just literally writing down what it means to fit into that diagram. You're asking for a formal group law such that when you reduce... So, questions about this? Okay, so here's the theorems. The theorem of Lubin and Tate is in two parts. First, this thing was a groupoid, but it turns out that it's a set. So first of all, def gamma takes values in sets. In other words, any isomorphism covering the identity just is the identity. It takes values in set. And second of all, as a functor from commutative these types of commutative rings into set is it's co-representable. And it's co-represented by a ring called the Lubin-Tate ring, which I'll write as E k gamma of 0, and it's non-canonically isomorphic to the Witt vectors, which I'll tell you not to be afraid of in a second, and then power series in n-1 variables. And so the Witt vectors, when k is, say, fp, then the Witt vectors of k is the p-adix. And when k is fp to the n, then you've adjoined some roots of unity, and the Witt vectors are the p-adix adjoined those same roots of unity. Okay? So this is the theorem of Lubin and Tate. That there's a universal example of a ring with this property. And then the identity map classifies an actual deformation, and so there is a formal group law over this thing. Of where? Right, so def gamma is going to take in one of these, a ring equipped with a map to K, whose residue field is K, and then the objects of this groupoid are formal group laws over that ring, which reduce mod the maximal ideal to the formal group law you started with. And then maps in this category are isomorphisms of such formal group laws, which reduce mod the maximal ideal to the identity. What are the source and target? So def gamma is a functor from the, I see, sorry. This is confusing. Maybe this is maps too. So given, you're right, sorry about that. So given a complete Ethereum local ring, then I get a groupoid. This is that groupoid. Sorry about that. That is confusing. So def gamma itself is a functor that takes in rings like this and spits out groupoids. And this is how you evaluate it on a single such ring over K. Does that make more sense? Or? Okay.
Yeah, how is the thing on the right groupoid? That's still confusing.
Where am I looking? Sorry.
So
right, yeah.
somehow you get a groupoid out of this, the input ring?
So this is a groupoid. Its objects are formal group laws over R, which reduce mod the maximal ideal to the given one. And its morphisms are these isomorphisms, which are the identity mod, the maximal ideal. Objects and good? Okay. Okay. All right, I'm almost done. I just want to say, okay. So the point is, so E, K, gamma, 0 has, in particular, carries the universal deformation because it represents the thing, that functor. So it carries the universal such deformation of gamma. In particular, that's a formal group, i.e. a formal group law. So we have a map from mu star to E k gamma 0, And for reasons, so you can make these reasons algebraic, but for now let's just do an ad hoc thing. I want an even periodic cohomology theory in a second, so I'm going to add in just a formal generator in degree, 2, and then invert it. So this is an even periodic graded ring, and I'm asking that this map extend to a graded map. So the point is that this is Landweber exact. So we get a cohomology theory, which is called EK gamma, which depends on this field K and this choice of height n formal group law. We get a cohomology theory called either Lubin-Tate theory or Morava E theory. But now, notice that the groupoid that I was using was morphisms which cover the identity morphism of K gamma, of the pair K gamma. But this whole story is natural in K and gamma. In particular, if I have an automorphism of the pair K gamma, then I get an automorphism of EK gamma. So automorphisms, strict automorphisms of gamma over K produce automorphisms of the universal deformation by naturality. I said strict. Oh, you don't think I need strict? All right, that's fine. Either statement is true. Great. So good. So this produces automorphisms of the universal deformation by naturality. Let's give this thing a name. So aut K gamma. Do I need to talk about the Galois group? Can I just call this thing? Okay. I'm going to call this Gn, which is the Morava stabilizer group. And this is acting on everything. So Gn acts on EK gamma. And that's filling in. So I found my fuzzy point here. But remember, this picture didn't tell me about the isomorphisms in my groupoid. So I have this fuzzy point, and then I also have all of these paths from this. Oh, this is pretty. A path from the from the point to itself for every automorphism of the point. So I really get this flower. And this flower is the data of the pair, which is EK star. Let me just put this acting on EK star together with this action of the Morava stabilizer group. And what is the cohomology of a stack that looks like a flower? It's the group cohomology of the group with coefficients in this representation of the group. So this is the cohomology of the formal neighborhood of K gamma in MFG. And so let me draw a diagram and then I'll stop. So the thing that we were after is we were trying to compute the cohomology of MFG, and we were going to do it by Meyer-Vietoris, and so we took an open neighborhood around each point, and we just found an interpretation of the cohomology of a neighborhood of a single point in terms of group cohomology. And that's going to remember a piece of the cohomology of MFG, right? I can restrict cohomology classes to this open neighborhood. So this is the cohomology Gn EK gamma star. And we know that this thing is trying to approximate the homotopy groups of spheres. And there's a question of whether or not this thing is trying to approximate something. And it is. This thing is trying to approximate precisely the homotopy groups of the Kn local sphere. So we now have this procedure to solve all problems in homotopy theory, which is first of all, you go ahead and pick a prime and hope it's not 2. And then you pick a height and hope it's 1. and then you compute the group cohomology of this humongous group, which is why you hoped your height was 1. And then of course the spectral sequence should collapse, so that'll be no problem. And then you got the homotopy groups of your Kn local sphere, and then we had this procedure for gluing together the answer for all of those things, which is that if I can inductively compute the Ln localization of the sphere, Len, Le, those are the same. Those are the same, but yeah, but I didn't say that, but okay. Yeah. So we had this pullback square, which says that inductively, starting at n equals 0, we can just compute each of these LKN things and then glue them up together, and then we're done. So in the rest of this conference, we'll hear about how far we've made it on that program. Yeah. Yeah, sorry.
So I thought that Morava theory, as you defined it right now or before, should see like not only one point in its neighborhood around it, but 0 to n together, an open set that contains all of these.
Yeah, right. So that's what's misleading about my flowery picture, is that this universal, you can deform a height n thing like all the way down to a height 0 thing, for example. So the flower gets caught in the wind and kind of sees all of the heights before it. So I don't know a good way to draw this picture, but it needs to be the case that an infinitesimal neighborhood around one of these far points automatically includes the preceding points. If someone can come up with a pretty way to draw that picture, that'd be helpful. By En. Oh, yeah, that's another confusing point. Yeah.
Can you repeat Paul's question?
Well, so I never used En star of x, which is maybe a useful point, but yes. Oh, the question is sometimes when people use this cohomology theory, Ek gamma, which if you don't want to talk about K and gamma and just want to remember the height, you call En. So sometimes people will write things like En star of x. Or they'll drop n too, and they'll just write E star of x. And a lot of times they mean, the thing is that this has some topology, En star is some complete local ring. So it has some like adic topology. And so it's a bad idea to like tensor together two complete looking things. You usually want to tensor together and then also complete, right? Right? Okay, so the analog of that in homotopy theory is that you're supposed to take En smash x, and then you're supposed to take its Kn localization, which remember was a type of completion, and then you're supposed to take its homotopy. So maybe, I don't know if that helps to answer your question. You're sort of, you're sticking it back in this infinitesimal, you're never letting it leave that infinitesimal neighborhood, I guess. Is that what you wanted me to? Okay. Other question? Yeah.
In this topology, En is also where we have cohomology,
Yeah, I also didn't say that. Yeah, so I'll just repeat the question. Right. So we're pointing out all the lies in my talk, and one of the lies is that this is some type of group cohomology, but this is really a profinite group. So this is supposed to be continuous group cohomology. Thank you. Yeah. So I'm supposed to remember the topology. I'm supposed to take continuous cochains on the group and so on, whatever. Yeah.
Can you say something else? Or I think you said this was in your talk, but so what's the significance, or what does it mean that this functor depth gamma takes values in a set?
Yeah, so that means that the only isomorphisms are the identity. It's sort of a weird thing. It's like if you have an isomorphism covering the identity, it just is the identity, which is, again, confusing. It's I don't know, it's a setoid. There's at most one morphism between any two objects. Yeah. It's equivalent to a set. Yeah.
So you said before that the MU localization of the sphere spectrum is again the sphere spectrum.
Yeah.
Can you hint why is that true? Is it solved when you manipulate theorem?
Oh no, so it's much less technology than that. So it's just in general true that if you have a connective if you have a cohomology theory which doesn't have homotopy in negative degrees, and you have a spectrum which also doesn't have homotopy in negative degrees, you can probably get away with less than this. Then the localization of the spectrum with respect to that cohomology theory only cares about pi 0 of the cohomology theory. That was probably confusing. So if you're trying to compute LE of x, and you know that E and x are connective, then this is just L pi naught of E of x, and pi naught of mu is z. Probably x just needs to be bounded below, and maybe you can get away with less. But yeah. So it's just that. This is in Bousfield's original paper. Any other questions? Yeah.